It's a mean value theorem, continuous on the closed, differentiable on the open. Take a look at that. What you need to do is put into words what you see. One is that there exists an input. Now, by the way, we keep going over this, and I just gave you the answer, but what is C, an input or an output? An input. So there's a value C, an input value C in the closed interval, open interval. Okay, that we're sure of, such that, and put into words. What words do you associate with this? F prime represents what, Mesh? Okay. The derivative of f of x at x equals c. Now, the derivative, let's go over that again. I mean, we can't go over this enough. And this is what you're going to remember 10 years from now. The derivative is what? In one word, slope is a value, right? A single value. If I say the slope of the line is 4, it's a single value. Okay, so the slope of a line tangent to this curve at this point is a single value. So the derivative is this. What is this? Yeah, I mean, you could read it that way, but let's think about what is, I mean, put another name to this. The slope. The slope of what? Oh, a line, right? What kind of a line? Are you sure it's tangent? What do you mean, just a regular function? I know you all have, you're on the right track, but let's pull it all together. If all you were given, let's put it this way, is this, you would say, oh, that slope of, would you say it's a tangent line? Just a line, right? Okay, the slope of a line connecting what? Connecting what? 2 points, right? What 2 points? Yes. Yeah, connecting, well, let's put it this way, points A and B, this is where x equals A and x equals B, okay. What's another name for the slope of the secant? Say it again. Average rate of change, which means that on an average, okay, the rate of change of what? What part of the function? On an average, what value, what part of the function is changing predictably? The input values or the output values? Keep in mind, we're always doing something with the input and asking the question, what's happening to the outputs? Okay? So it's the average rate of change of the output values. On an average, the output values are going to be changing in a predictable manner. Every unit increase in the input, the outputs are going to be increasing by 2 or by 4 or by pi or whatever. Okay, that's what average rate of change is. Now, go over here. That's not average rate of change. Let me do something while you think about it. What is it instead? It's what? Instantaneous rate of change. Okay. Instantaneous rate of change. Okay, and what does that mean to us then? Instantaneous rate of change. So we're saying that at a certain point, the outputs are behaving in a predictable manner. At a point, not over time, not between A and B, inputs A to input B, but exactly at C, here's what the outputs are doing. So we've got now, and by the way, if you had written this statement back in chapter 3, when we were talking about derivatives, I would have said, no, that's incorrect. The derivative is not slope. It's the limit as delta x approaches, all that stuff we had to go through. Okay, so this is a little different. This is a theorem, and this is saying that if the function is continuous on a closed interval, differentiable on an open, there's a number of input value in that interval where the derivative has the same value as the average rate of change over the whole interval. That's what it's saying. Okay, now, I moved some stuff so I could write more. And again, I don't remember if that's just 36 or not, so we'll scratch that out for now. It says, sketch the secant to the graph through the points A, f of A, and B, f of B. If you got that on your paper, if you don't, just, draw a curve that looks something like that. And, whoops. There we go. I'm trying to find, there we go, the magic pen. There we go. Okay. That, if I draw, let's see if I can draw a line through that. There we go. Not bad. Okay, so there's my curve. There's my secant line. I'll get my words here in just a minute. So this is my secant. I'll go back to the regular pen now. This is the secant. And we can find the slope of the secant to be something, okay, something negative. Now the question is there any place on this curve where the tangent would have the same slope as that secant line? That's what we're looking for. So let's see here. If I clone that, can I move it parallel to it and make it a tangent? Yeah. This point right here, this value right here is a point where the tangent to the curve would have the same slope as the secant connecting the endpoints. Is that the only place? Well, let's see. If I move that straight up there, it looks like we have a second one up there. And so we'll call this C1. We'll call this C2. There's actually, it looks like, a third point right down here that the secant line actually touches the curve too. So we could probably call that then a third point, C3. So there are 3 points in that interval where the tangent would have the same slope as the secant. That's what the mean value theorem is all about. The mean is an average. You knew that. Mean, median, mode. Average, median, and mode. So when we average out the outputs, and we say that on an average, the outputs are dropping so many units for every 1 unit increase in the input, then there's 3 other places on here that would have the same rate of change of output. Okay, so let's see here. Determine whether or not we can use the mean value theorem to this function on the closed interval from 0 to pi. If you can, then find all values of input within the open interval such that the mean value theorem can be applied. So first thing, ask the question, is f of x continuous? That's a u there. Continuous on the closed interval from 0 to pi. What do you think? We go up here and highlight our function so we don't lose it in the midst of everything. Is that function continuous? No? Is sine function continuous? Where? Everywhere. Okay. So if I add a continuous function to another continuous function, do I have a continuous function? And the answer to that is yes. It's continuous everywhere. Okay. Is f of x differentiable on the open interval? We'll put a little reason up here. Yes, because the sine curve is, the sine function is continuous everywhere. What about differentiability? Is it differentiable? We've got a derivative for sine, right? So we could find the derivative of sine 2x. So the answer here is yes. You know, sine x, sine function is differentiable everywhere. So therefore, the sum of 2 differentiable functions is differentiable. Okay. So there's the only criteria we have, that there is continuous and differentiable. So can we apply the mean value theorem on that? Yeah. There's no other criteria. Remember, we don't have to worry about does f of a equal f of b. In fact, if f of a equaled f of b, what would happen to our, yeah, so it could be 0. So we don't, that's not a part of this one. Okay, so yes, we can apply that. So determine that, and we can say, yes, that's true. Now, find all values c in the open interval such that this happens. So what's the next thing we need to do? Go ahead, Casey. Oh, still thinking? Okay. We want to prove this is true. So what do we need to do? Okay, so find the slope of the secant. Okay, so determine f of b minus f of a divided by b minus a. Okay, so that's going to be f of pi minus f of 0 divided by pi minus 0. And